So the key point, I repeat, is that we are going to try to communicate with each other, and so your lectures, your contributions are meant to set the scene for the discussion. Without further ado, let us start with Nussbaumer from Zurich, who's going to set the scene in the way that will tell us about the history of cosmology, so that we're all on board with it.
Well, good morning. I was given 40 minutes, which then last night were shortened to 30.
You can take 40, but we will interrupt you.
Okay. Anyway, 1927, you know, Georges Lemaître discovered the expansion of the universe. Not only that, expansion of space, a crazy thing. And let's see, how did one look at the universe in those days? It was the time, I jumped to 1917, when Einstein actually inaugurated modern cosmology, and it was the time when Lemaître probably got his first glimpses at cosmology. The Milky Way was seen as a huge disk of millions and millions of stars, and these nebulae here, discovered since about the beginning of the 17th century, one wasn't sure whether they belonged to that Milky Way or whether they were Milky Way in their own right, island universes. The debate was open in 1917. In the middle of the 19th century, spectroscopy had been invented. The investigation of stellar light showed that one of the last vestiges of Plato and Aristotle, namely the fundamental difference between the earth and heavenly bodies, did not exist. They all exist of the same matter. Since 1912, Wester Schleifer had found many of the majority of those nebulae he investigated large redshifts in the spectra, which meant, in those days, they were all running away from us. No explanation for that. In 1900, Karl Schwarzschild dreamt of a geometry for the universe which was different from the geometry we are accustomed here. He thought it could be a space that somehow wrapped on itself, came back on itself, and it would be a finite universe. And the great thing about the finite universe would be that one day astronomers would know everything about the universe. That was the great thing. So when Einstein in 1917 applied general relativity to cosmology, he had a fundamental equation, which was this one here, and on the left-hand side is the structure of space. So if you send a beam of light out, will the beam of light go in a straight path or will it take a curved path? That's described on the left-hand side. On the right-hand side, he had matter and the energies which were responsible for that structure. And Einstein, of course, only knew about gravitation. Now, gravitation, any particle attracts every other particle in the universe, which, of course, means the whole thing will collapse. But Einstein didn't want a collapsing universe. He wanted a universe that was the same since minus eternity up to plus eternity. And for that reason, he invented, against gravitation, a kind of cosmological repulsion. And this is his famous cosmological term there. When he did that, he really obtained something that approached the dream of Schwarzschild. He had a universe, a curved universe, a finite universe. And if you build a house, you ask the architect to show you plans. What does it mean, the plans? 3 dimensions are projected onto 2 dimensions, and we go one step further. We project the space of the whole universe into 1 dimension. So, if the galaxy A sends a beam of light to galaxy B, it passes and it goes out to infinity if the universe is constructed in the normal way we imagine space to be. But that wasn't Einstein's universe. Einstein's universe was different. It was, if A sends a beam of light towards B, it will not go on a straight line, it will go on a curved line. path, and if you wait long enough, it will meet you from the back. So, and this here is direction of time. So as here we sit here, fixed as these two galaxies, and time goes on. And that then was Einstein's curved, steady, stable universe. Okay, a few months later, De Sitter came up with a different model. He said, look, there is so little matter in the universe, we can treat it as empty. Well, it was a bit cheeky because it wasn't quite empty. He actually kept the cosmological constant, and when he did that, it looked as if he could explain the redshifts of Schleifer, which Einstein couldn't. But people like Eddington, and later on also Robertson, famous cosmologists, they didn't quite trust. They said it was one couldn't really see the physics in De Sitter's. 1925, Lemaître would show why. Anyway, this was the universe, together with the picture you have seen before that Lemaître made when he started. Huh?
The physics is wrong there as well.
That's the cosmological constant.
On the second line.
Which he kept, but he...
No, but on the second line there, the redshift relation is wrong.
Oh, yeah. That's what you get from De Sitter's universe. The redshifts would be quadratic with space.
No, if you do the calculation wrong, yes.
Hmm?
If you do the calculation incorrectly.
No. I'll show you why that. Well, the whole thing was was really not correct. I'll show you. So this was Lemaître's picture of the universe when he started, and in 1925, Lemaître had his first go at cosmology, and he looked at this. Lemaître then he went to England. He was lucky to study with Eddington, who was one of the very few to really understand general relativity. And then he went on to America, where he worked with Harlow Shapley. Shapley was the chap who showed that we are not close to the Milky Way, but we are rather some distance away of the Milky Way. Shapley was of the opinion that all those nebulae you have seen belonged to the Milky Way. Then, in 1925, Hubble showed that this was not correct. One had always that was a matter of discussion. That it was not correct, that at least 3 of these nebulae were far outside the Milky Way. So it was clear the universe is built of those nebulae. And nebulae, each one containing millions of billions of stars, and the Milky Way is one of those. And here comes Lemaître with his, when he looked at De Sitter's universe, he discovered that De Sitter violated a principle of homogeneity. It means that De Sitter treated the other nebulae different, physically different from the way he treats our place, the Milky Way. And when Lemaître corrected for that, he agreed with De Sitter's fundamental assumption there is little matter in the universe. Then he found a universe that was not curved as Einstein's universe or De Sitter's universe had been before, but a flat universe the way we imagine space to be. And he said we can't accept that because that leads us back to the Euclidean space and the impossibility of a universe, infinite space, filled with matter which cannot be but finite. And now this is no longer physics, this is philosophy. And I wonder whether he was influenced by Thomas Aquinas. So we certainly have people here who know about it, and they will tell us in the discussion what they think about that. Anyway, 2 years later came Lemaître's masterstroke. He had a connection between theory and observations, and he said in a dynamic universe there is a relationship between the redshifts observed in these galaxies and the distance. That's the redshifts give a velocity, how fast something goes away from us or comes towards us. And he said, well, this means that the universe, these redshifts are due to the expansion, not galaxies running away from us, but galaxies standing still in space, but space is expanding. Space itself is expanding. And so here you have the Einstein, and then here you have De Sitter. Here you have Lemaître, and that was Einstein. And 2 years later, Hubble came up with something very similar. Well, not really similar. Hubble found from observations that there was such a relationship, same as Lemaître had found. But Hubble wouldn't give any explanation. He said explanations that's for the theoretician, not for us. And okay, I think I have to hurry, as I was told. I have 30 instead of 40 minutes. That was then Hubble's contribution, which is very often falsified, that Hubble discovered the expansion of the universe, and this is really rubbish.
It's like
The breakthrough for the expanding universe came, well, you know, this publication of Hubble's was 29, Lemaître's publication was 1927, and in 1930, two of the great scientists in cosmology of those days that were De Sitter and Eddington. They, in a talk in London, De Sitter marveled about what Hubble's observations of these redshifts, what it meant. Lemaître saw that and immediately wrote them a letter and said, look, I have a solution. And both Eddington and De Sitter were enthusiastic about it. They said, that's something quite new. You know, a new universe in expansion. That's enormous. And in a really unprecedented move, monthly notices published in 1931, a translation which wasn't quite complete. Important omissions, because Lemaître, it was awful. He was a terribly modest chap. Well, so then Lemaître's suggestion was a universe, well, was it without the beginning? He said it could have been an Einstein-stable universe in the past, and both Eddington as well as Lemaître tried to find solutions. Eddington's group, but they didn't succeed. And then suddenly Lemaître comes and says, look, actually, there could be that the universe started from one single atom, an enormous atom, the matter of the whole universe being united in one atom. That was, and then off it went, but it's not that the particles, the matter of the universe went into a space, but it created space. These particles, they created space. So you can imagine this enormous atom broke apart, but at an enormous space, the space itself expanded. So that's the Big Bang. 1931 by Eddington. Lemaître showed that to Einstein, and Einstein was about the only one who had a close look at it. He also sent his paper to Eddington, but Eddington, by some oversight, didn't take note of it. Then Einstein and De Sitter teamed up together. They said, well, okay, if you can't have a stable universe, then what's that cosmological constant? Einstein had introduced a cosmological constant because so that the repulsion, so that the universe wouldn't collapse, a repulsion term. And now, if it is expanding anyway, we don't need such a term. It's really anyway artificial, Einstein said. He never liked it. He didn't like it. So let's do away with it. And also this curved universe, curved space, it's an awful thing. If we have an expanding universe, it could be that expansion is such a way that we have a flat universe, which, according to our way of thinking, a flat universe. Okay, and this universe is really, well, they saw that it didn't quite fit the observations, but that wasn't all that serious because the observations were rather insecure. So they could say, well, if you have better observations, it will fit all together. And then, so the simplicity of this Einstein de Sitter universe was such that all the theoreticians were enthusiastic about it, and it was the universe that was valid until about close to the end of the 20th century, actually. And Lemaître's model was not quite discarded, but slowly went into oblivion. Okay, Lemaître realized that if he wanted to defend his model, there would be 2 points he had to show. That was, what's about the elements? How did the elements come into the universe? And he said, well, that's very easy. We have, to begin with, we have this the primeval atom. All the matter of the universe united in one big atom. And this, bang, the Big Bang, decays. And all that is left from this one big atom are now the 92 elements which we have in the periodic table. So, okay, problem is solved. However, that was also the time when nuclear physics started to develop, and they showed that, and also when it became known that hydrogen was the most abundant element in the universe, which before hadn't been the case. Before, heavier elements were thought to be the most abundant one. Now, one saw through spectroscopy that hydrogen was the most abundant element. And so you see, Lemaître came with a top down. We have an enormous, one big atom containing all the matter of the universe, decaying. And then the others, they said, no, come on. To begin with, we had hydrogen, nothing else. And hydrogen then developed somehow inside the stars. And it was Bethe in 1939 who showed that hydrogen can fuse into helium, but the problem was not into heavier elements, here he thought. And this then gave Gamow the idea. Gamow believed, because at that time, Lemaître's Big Bang wasn't generally accepted, but Gamow believed in it. Gamow believed in it, and he said, okay, so it could be that a very early universe, very early means first seconds, there perhaps the heavier elements formed. The universe existed of hydrogen, and then the heavier elements formed. That was his idea. And, well, it's a long history, I have to cut it short. That was Gamow's, not only Gamow's, but the whole group around him, how they thought that the elements came into existence, practically in the Big Bang. So Gamow had also a Big Bang, just as Lemaître, but really a hot Big Bang. That was essential in Gamow's play. But later on, Margaret and Jeff Burbidge and Fowler and Hoyle, they showed that actually it wasn't necessary to have such a Big Bang. They left it open. Also, of course, Hoyle wanted a steady state universe where there was no Big Bang, because all the elements can be formed inside the stars. Okay, so that That was one point in Lemaître's. He had the top down, the primeval atom, decays, and all the elements which you have on Earth and in the universe formed. The others said, no, they formed either inside the stars or already at the very early universe, out of hydrogen. The second thing was, if you have in Lemaître's decaying primeval atom very homogeneous, how do inhomogeneities like the galaxies? Today we have galaxies, so the universe is actually highly inhomogeneous. We have a lot of individual galaxies. How did that form? Well, for Lemaître he said, well, actually we have the very beginning, the Big Bang, the elements form, but then there is a kind, when the universe expands, there is a kind of, comes a kind of equilibrium between the gravitational attraction, which breaks that expansion, which slows the expansion down, and the cosmological constant of Einstein, which tries to push it apart. There is a kind of equilibrium, and in that equilibrium, vast regions can form where the density is a bit higher than in other places, and which, although that region as such takes part in the general expansion, the region itself does not expand. And in that region, gravitation can form galaxies. So the whole region becomes a cluster of galaxies. That was Lemaître's idea. That forms here, in that region, quasi-equilibrium. And he thought we are now in this here, in this direction is the size of the universe, how big is the universe, and this is time. And he says now the universe is expanding, it becomes bigger and bigger and bigger. Through the cosmological constant, it's pushed apart. The others, they said, competing, they said, well, yes, at the very beginning they also believed in a Big Bang. Gamow believed in the Big Bang. They said that here there could be, but they didn't have such an equilibrium because Einstein and De Sitter, when they had their universe, they had kicked out the cosmological constant. They said we don't need a cosmological constant. And in Lemaître you had the equilibrium, or nearly equilibrium, between gravitational attraction and cosmological repulsion by the famous cosmological term of Einstein. And they didn't have such a cosmological term, so it was just expansion, and it was shown that here you can't, Lifshitz showed that in 1945, you can't really form in such an expanding universe, you can't form these inhomogeneities which lead to galaxies. So that was open, and that question was open, and well, there were some lone figure like Bondi, who in 1952 and again in 1960 said, well, among all the relativistic models, it seems that Lemaître is the most convincing, but he was a rather lonely voice, and the large majority of astrophysicists, astronomers, believed in what Joe Silke will tell us later on about how that business evolved, that one of the overwhelming difficulties of realistic cosmological models is the inadequacy of Einstein's gravitational theory to explain the process of galaxy formation. And Silke, as was the general trend there, also assumed an Einstein-De Sitter universe, and thus cosmological constant equals 0. And it will be I'm really looking forward to Silke's talk when he tells us about further evolution. Okay, what's today's idea about it? Well, if you go to Google, you Google and say, hey, model of the universe, you'll get something like that, which shows here the Big Bang, as in Lemaître and later on Gamow. Gamow then had a really hot Big Bang. Lemaître just had the Big Bang. it goes apart, but it is decelerated by gravitational attraction. But you know, when bodies move apart, the gravitational attraction becomes smaller and smaller with distance. And then the cosmological constant intervenes and pushes the universe apart. So what you see here, that's time, and each ring is the size of the universe at a given time. So you see the universe is expanding, and now it is expanding in an accelerated way. That's today's. And it corresponds to what Lemaître had already in 1933. There are, of course, some fundamental differences in the physics, but that's another matter. Well, what are the differences? Well, first of all, in 1965, you see, just 1 year before Lemaître died, the cosmological background radiation was discovered, but for that question here, even more important, 1990s, when new instrumentation showed of the cosmological background radiation, showed the information which gave us news about the very, very beginning of the universe. That was a very important 1990s background radiation, new instrumentation. And we'll also hear about dark matter, of course. 1933, Zwicky had found, well, look, in clusters of galaxies there must be matter which works through gravitation. But we don't see it, we don't know what it is. Well, Zwicky wasn't taken all that serious to begin with, but later on, particularly after the 1980s, this existence of dark matter was seen about everywhere. And one didn't look for it anymore just for normal matter, which we know, but an unknown kind of matter. And these two were really the important ingredients. That one came back, and that would be that. Here you have time, here you have the size of the universe. The Einstein Decider, as time goes on, the universe just grows bigger and bigger, but you see, in such a way, whereas Lemaître goes up in an accelerated way, whereas here the speed of expansion is becoming slower and slower. So that's modern, today's. But I'm looking forward to the next two talks. They will tell us more about that. So now to a completely different theme. Why was Lemaître nearly forgotten? Well, first of all, his modesty. When you read his papers, you hardly ever see a citation of his own work. When Einstein had been about the only person who had looked at the 1927 paper of Lemaître, and they met in Brussels at the Solvay Congress, and you probably know Einstein's famous reply to Lemaître, well, formally your work is fine, but physically it's abominable. Genius can err as well. But at the same time, Einstein had told Lemaître about Friedmann. That Friedmann already, the Russian, in 1922, had developed a similar formalism. And from that moment onward, Lemaître never referred to his own work. He always referred to Friedmann, or if he had to refer to his own work, he just said, it has been shown. And such modesty, of course, I think probably none of the physicists or scientists in here would be that modest. Anyway, I wouldn't. This self-effacement, it didn't help to spread his faith. Then second, his clinging to the cosmological constant. Lemaître and Eddington were about the only two who really said, yes, the cosmological constant. Lemaître said it's actually one of the biggest things that Einstein did, this cosmological constant. And all the others, because Einstein didn't like it,
it made him appear old-fashioned, and old-fashioned, of course, is, no, you're out. You're out. You mustn't be old-fashioned. Then the laziness of those writing history of astronomy. Already at Gamow, I found, after Hubble announced his discovery of the expansion of space, absolute rubbish. Hubble never announced something like that. Never. And I found this citation also in a book that had a new edition 2001, still there. And then something to which Sandage drew my attention. He said there was very efficient advertising of the Hubble myth by interested institutions, and he thought about Carnegie. And I give you an example. We have here Einstein went to Caltech in 1931 at the invitation of Millikan. They wanted him over there as professor at Caltech. And of course he also visited the other scientific institution like Mount Wilson. And here you see him together with Hubble on Mount Wilson. And what are now later descriptions of that picture? Hubble shows Einstein that the universe is expanding. Okay, now we are in front of a kind of St. Paul's revelation. No, Hubble shows Einstein. Must be great. Or 2 months with Hubble were enough to pry him loose from his attachment to cosmological constant. Or Einstein exclaimed after his Mount Wilson visit, if there is no quasi-static world, then away with the cosmological term. Yes, Einstein said that once, but it was on a postcard to Hermann Weyl in 1923. What are the facts about Einstein's conversion from a static to the expanding universe? Actually, I think it's very simple, because Einstein helped us to find out. He had a diary for those days. And in his diary, he mentioned conversations he had, what occupied him when he was there in Pasadena. And he mentions Zwicky, he mentions, of course, Tolman. Tolman, another great scientist, a cosmologist. He really became friends with Tolman. He mentioned St. John, another observer, which was very important to Einstein because St. John observed the sun, and it was the question about the gravitational redshift. He never mentions Hubble. The diary of those days never mentions Hubble. If he produces such a marvelous insight, one would think it should enter that diary. So what are the facts? Well, the facts are that in January 1930, De Sitter gave the talk in London about the publication of Hubble, where they said, we don't understand. Then Lemaître sent them his publication of 1927. Both Eddington and De Sitter, they were full of enthusiasm. They said, that's what we have been waiting for. That's the true solution. And they both published in different journals, monthly notices for Eddington, the Bulletin of the Dutch for De Sitter. And 1 month after Eddington's publication, Einstein visited Eddington, and Einstein stayed with the Eddingtons in Cambridge. He stayed with them, with Eddington and his sister. And there is no diary of those days, but it's impossible to think that Einstein and Eddington wouldn't talk about cosmology, and I'm sure what happened there, that Einstein was updated on astronomy because Einstein notoriously, he didn't know what was going on in astronomy. And Eddington, in his publication, had shown that actually Einstein's solution of the static universe was unstable. And so for any theoretician, if then is found out that actually his solution is unstable, that one day it either has to go into expansion or into contraction, he knew, okay, finish with my theory. So Eddington must have updated Einstein on that. And the switch of Eddington and De Sitter, a good friend of Einstein's, that they both had switched to Lemaître's expanding universe, and third, Hubble's publication confirming Lemaître. So I think that's the solution why Einstein switched, and not sent Paul's conversion up there. Now, how did Lemaître influence the history of cosmology? Well, there are certainly two basic and lasting. First, Lemaître discovers the expansion of the universe. And in 1931, Lemaître proposes the sudden birth of the expanding universe. You know, that's also something crazy. He said, okay, if there hasn't been a stable universe in the past, then perhaps we have to accept that there was a beginning to the universe. Eddington didn't like that. Eddington said, oh, I can't think of a beginning. It was a bit too close to the Bible. Whereas Lemaître never wanted to include the Bible in his science. Lemaître's cosmology could also have been done by an atheist. And essential insights, he spotted De Sitter's ill-chosen coordinates. De Sitter's physics were fine of the empty universe, but the coordinates he chose gave all the trouble. Then he also started investigation into the emergence of inhomogeneity. How could galaxies form? That actually was started by him. You had to go back rather far into the past. And whereas the cosmological constant, which Einstein kicked out, Einstein introduced as a kind of mathematical gadget. Whereas Eddington and Lemaître both said that this is a basic constant of physics. It's something very basic, a cosmological repulsion as against gravitation, which is cosmological attraction. So I think we have a kind of duty. That Lemaître's discovery of the expansion of the universe is not stolen from him and attributed to Hubble, which is still done in some quarters. It's no longer done by the Hubble Space Telescope. I think they were finally converted, but it's still done. And to show how important Lemaître's discovery was seen at the time, I'll show you to end with. I'll show you what one of the big shots of those days, De Sitter, what he said about Lemaître's contribution. He didn't mention Hubble, he said, the way out of this dilemma, the impasse reaching cosmology around 1930, the way out of this dilemma has been shown by the Abbé Lemaître, whose brilliant solution, the expanding universe, was discovered by the scientific world about a year and a half ago, 3 years after it had been published. There can be not the slightest doubt that Lemaître's theory is essentially true and must be accepted as a very real and important step towards a better understanding of nature. So I think that gives justification that we should, to whom the discovery of the universe has to be attributed. Thank you.
Great, thank you, Harry. Yes, I have a question. You mentioned this paper by Friedman in 1922,
yes.
And the fact that Lemaître. So what was in that paper? What was,
Friedman. Well, Friedman, he discussed mathematically difference of. Friedman went further than Lemaître. Lemaître knew the redshifts. Lemaître developed actually, there was Einstein's paper before, and Lemaître said, look, if we take Einstein, but we allow the universe to be dynamic, then we get something different. Friedman didn't do that. And not because Friedman wouldn't have liked to do it, but Friedman thought at the time that astronomy was simply not yet good enough to give an answer. So Friedman stayed with showing what different models did. It was a great work, Friedman, and Lemaître was quite right to cite Friedman. But the expansion of the universe, that wasn't Friedman's idea.
So in Lemaître's primeval atom model that he showed us, before the primeval atom, clearly it was starting from zero or whatever. How did Lemaître address that beginning pre-primeval atom?
Well, in the 1927 paper, he simply said, well, there are different solutions, but one solution would be you start with an Einstein stable universe. And then, through some process, physical process, it starts to expand. And both Lemaître himself and Eddington's group, they tried to find physical processes that would start that expansion, but it somehow didn't work out. And then came Eddington in 1931, very early, and gave a talk about the end of the universe. And in this talk, he said he couldn't think of a beginning of a universe. The universe had always existed. And Lemaître reacted immediately by a small article in Nature, where he said, well, he could very well think of a beginning of a universe where all the matter of the whole universe had been collected in one big atom, which then by sort of radioactive decay started to decay at enormous speed, and decay, and today just the 92 elements left. And there was a short period where Lemaître even thought that stars could have formed during that decay process, but then he quickly gave that up. So that was a bit the story of the way away from Einstein's static universe, where they said, well, there can't have been such a static universe. Can't have been. So if there can't have been a static universe, why not have a beginning? And of course, to Lemaître, it was quite clear that he came up with some hypothesis, but that quantum theory would have to answer the question of what happened at the very beginning with that primeval atom, how that should work. And that was then taken up by Gamow. And Gamow came then and said, well, I don't want such a primeval atom which decays, but I want a primeval gas, a kind of, as we think of it today, and that was then the hot. So Gamow said, well, at the beginning there must have been a very hot universe, very dense, and then all the heavy elements could have formed in there. Does that somehow answer?
Here, I guess I just would like to reiterate the whole idea about Friedman or Hubble being the originators of the expansion of the universe is a false premise, mostly because, first of all, Friedman did not have the observational data that Lemaître had access to in terms of Hubble's distances and Slipher's redshifts. And Hubble had no understanding of general relativity. He had no understanding of the theoretical basis for those solutions of Einstein's equations. So both were kind of handicapped by lacks of knowledge, which Lemaître had. And
Yes.
Really the crux of the argument behind giving him this.
Yeah, Lemaître, of course, had the advantage in that respect that he both had very good theoretical knowledge, good mathematical, and then by working with Shapley for 1 year, he also worked in practical astronomy. So he knew the observations. He had the theory, and that was his advantage. Hubble
when you go through his paper, he never believed in an expanding universe. He never believed in it. And, but he didn't do much. He didn't do much to fight, or actually, Hubble is, in a way, it's a bit like Galileo, it's a bit cheeky, the way Hubble behaved. He never mentions Lemaître. He never mentions Lemaître. So he must have realized that Lemaître came 2 years before him with the famous Hubble relation. Expansion velocity equals linear proportional to the distance. And that Lemaître calculated even the concept of proportionality very close to what Hubble found. Lemaître came to about 600 kilometers per, and Hubble had about 500. So very close. Hubble never mentioned him.
Okay, maybe one more question, and then we can break him up.
It is cynical that the same story repeated.
Oh, actually, yes.
No, it is cynical that the same story which you mentioned repeated in the 1990s, where the cosmological constant was discovered again to explain the universe. On the one hand, you have the theory who explained, well, the theory of inflation,
Yes.
where lambda equals 1 was necessary. On the other hand, you have the observations of the age of the universe, which were inconsistent with just a closed universe but without cosmological constant. And in the 1990s, I mean, I remember that people developing inflationary theory, well, were not so much worried about the astronomical data. They said these astronomers, they have their ages wrong by a factor of 2, that happens. On the other hand, the astronomers were unable to understand the relevance of the theory behind inflation. And if Lemaître had lived in the 1990s, he would have predicted the 1999 discovery of the cosmological constant through observation. He would have, according to this reasoning, and I think it's fully true.
Well, there was also, in defense of the theoretician, I mean, the Einstein De Sitter universe is really theoretically beautiful. So simple. It must be true.
I'm not sure that's much of a defense.
I have just to comment. You have referring to the study, the Lemaître study of non-homogeneous inhomogeneity.
Yeah.
Yes, and there is some deep connection with this problem and the subject of his PhD thesis at the MIT.
Yes.
Because he studied a modern gravitational field essentially induced by a sphere field of non-homogeneous fluid. And in fact, we have not to underestimate the work done by Lemaître in this MIT thesis. Because in this thesis he discovered 2 particular cases, Einstein cosmology and also the Sitter cosmology. And he thought about some kind of interpolation, at this time non-dynamics.
Okay, I also...
Yes. And there is, connecting to this problem, there is also an historical mistake, because Lemaître spoke with Tolman at Caltech about this problem, and we call this model Tolman-Bourdi model, and in fact, Tolman referred to Lemaître, to the thesis. To the problem of study of non-homogeneous universe. Yeah. And in fact, Lemaître's name disappeared completely.
Okay.
And Krasinski, for example, has published a nice paper and book in which he said, well, the origin of this problem is in fact Lemaître and not Tolman.
I have to refer to your fine publication on Lemaître's life. There you said, his 1927 paper, my question is, didn't he publish it in the wrong journal? And he's of the opinion, no, it was just premature, but I don't believe that. I think if Lemaître had sent his publication to monthly notices, then Eddington would have been forced to have a close look at it, and Lemaître would have spotted the genius in that paper, the revolutionary idea. I think...
And the second short comment is about the influence of Thomas Aquinas or Lemaître. And I think Lemaître did never accept some actual infinity. He refused, he accepted potential infinity, but he refused empirical actual infinity. And the reason was that, in fact, he said, well, if the universe is really infinite, empirically infinite, then the human's mind cannot, in fact, grasp completely the universe. But I think this is related to, yes, some philosophical assumption.
Going back to Thomas.
Aristotelian, and yes. Because he cannot accept an actual empirical infinity. Yes. And he said this in the high-level atom hypothesis in the book.
Yes.
Well, this is what they call a finger as against a hand. A quick follow-up, if I may.
Okay.
Is it possible that this quotation is reflecting the paradox of Newtonian cosmology about homogeneous Euclidean space filled with gravitating matter?
Yes, I was also wondering.
This is Newton himself struggled, everyone struggles. Newton can't find gravity, in a sense, solves this problem, but could he have meant that when he said this? Is it possible?
Okay. Let's break for coffee. Thanks, Harry.